This is lesson 5, exercise 9D, traversable graphs, and this will be the last video that you'll have to watch within this topic. When we continue this, we'll be continuing this topic in face-to-face teaching back at school. The way to go for this one, very simply look into what a traversable graph is and the success criteria, very simply, to determine if a specific graph is traversable. Now, what is a traversable graph? Well, it has a trail that includes every edge in the graph. And so remember, a trail is going from one spot to another. Let's say we'll look at A, and we're going to go from A to B to C, and then go back to A, and then finish at C. Now it's traversable because we're not repeating any of these edges, but we're going over each edge once. And it doesn't matter if we go over the vertice again, but as long as we go over every edge, it's considered traversable. Now, not all graphs are traversable. This one here, this is traversable because we've got this trail route here, but it is impossible to find a trail in a graph within here that includes every edge without going over it again. And you can keep trying to see if that's the case. You can consider it one of those brain teasers where you have to try to go over every single edge, but you're always at most going to miss out on one. Obviously you can't repeat the edge again. So to see if we can identify if a graph is traversable, it has to be connected. And the connected graph is traversable if either all of the vertices are of even degree. And so remember, the degree of a vertex is just to see how many edges go to a specific vertex, and you get that number. If every single number, you get every single one, and you get all of them even, then the graph is traversable. You can do a trail of some sort where you can visit every single edge. And the other circumstances where exactly two vertices, and it's exactly two, it has to be specifically exactly two, not one or more than two, it has to be exactly two vertices, are of odd degree, and the rest are even degrees. Now, from this, it follows that a traversable graph will either have a trail, a circuit, or a cycle that involves the use of every edge within the graph. So you can either have a trail, circuit, or cycle. And if a graph has more than two vertices of odd degree, it's not traversable. So as soon as we go past and we have like 3 or more, it's not traversable. You can't visit every single edge. Now we're going to use these rules. We can see why graph 1 is traversable, and using these rules back up here, sorry, for graph 1. Using the rules, we can see graph 1 above is traversable. It has exactly 2 odd vertices A and C, and the remaining vertex B is even. So what this means is C vertex A, we've got 1, 2, 3. This is 3, which is an odd number. C is 3 as well, and B is 2. We have exactly 2 odd numbers, and this 2 is an even one. This satisfies this little explanation, meaning that this is traversable. But when you look at this one, all of these are 3. As soon as we hit more than 2 odd vertices, we know for a fact that it doesn't suffice to any of these characteristics, so it's not traversable. So the key component of determining if a graph is traversable is to identify the degree of each individual vertex. That is the number of lines coming from. I like to think of it coming to each vertex, not coming from. I mean, I know it's the same thing, but I'm consistent in that way because it can get kind of confusing when it comes to loops. Alright, so for each of the following graphs, we're going to A, determine whether the graph is traversable and state why, and B, if it is traversable, we're going to check by identifying a trail or circuit that traverses the graph. So, A, for IA, sorry, here we go, for IA, let's determine whether the graph is traversable and state why. So here we have 2, 2, 2, 2. So the degree of each one is 2. We've got 2 going to each one. All of these are even, so it satisfies that first one, all vertices of even degree. So to determine whether the graph is traversable, we're going to say yes, is traversable, and we're going to state why. All vertices of even degree. Whoop, there's an extra E. Why not? So all of the vertices are even degree. And the second thing we're going to check is if it is traversable, which in this case it is, we're going to check by identifying if it is either a trail or circuit that traverses the actual graph itself. So you got to remember that the difference between a circuit and a trail is just based on the fact of whether we're starting and ending at the same vertice or not. So in this case, because all of these are even, and you'll learn this in the next lesson, because all of these are even, I know for a fact that we can start and end at the same vertex each time. If we start here, we can go from here to here, to this way, back down, and then around and end, in this case here. So this is a circuit. It is a circuit because we start and end at the same vertex. Alright, for A, let's see the degrees of each one. So this is 2, this one here is 2, this one is 3, this one is 3, and this one is 2. So we satisfy the characteristic of exactly 2 vertices of odd degree, and the rest being even. Yep, that is the case. Here are the 2 odds, they're the evens. So yes, this is traversable. And in this case, exactly. Oh, it's running a bit slow. Exactly. I'm so glad this is the last video. Imagine if this happened to me while I was teaching at school. I would just be writing on the whiteboard and then it doesn't pop up. This term is delayed. Alright, I'm just gonna pause and wait until this pops up. Here we go, exactly. Spoiler alert, I actually had to write this in again. It's quite annoying. The only thing that popped up was that random line there. Okay, so yes, exactly 2 odd degree vertices. And in this case here, with B, we're going to state whether it is a trail or a circuit. Now, no matter how many times you do this, you won't go back to the same vertice that you start off with. And another key component is that you'll learn this in the next lesson. If it has exactly 2 odd vertices, you have to start at one of the odd vertices, and by default, you will always end at the other odd vertice. You can't start at an even vertice. You can try to see if you can walk every single path without repeating it, but it's not possible. The conditions are you have to start at an odd one and end at the other odd one. So let's start here. We can go, say, up this way, and go up to here, and then go down here, visit back to the one we started at, go up to this 2, and then go back down, and we end here. And obviously we can do this in the reverse process. We start here and here, but you can't start at an even one. You cannot start at an even one. In this case, this is a trail. All right, I. Last one. Oh my goodness, it's so delayed. Okay, so let's determine whether the graph is traversable. So this is 3, 2, 3. We got another one, 3. Oh, we got more than 2. So no, not traversable. And we have to say why. More than 2 odd degree vertices. So if it is traversable, which is not, so for question B, we can't really answer this because it's not traversable. So we can just write not applicable. And E. Alright, that's the last example for remote teaching. Last video that you'll have to watch, assuming that Victoria doesn't go into another lockdown in the middle of the term. And if they don't, this will be the last video you have to watch. Go ahead and check your log sheet, see which questions you need to do for this exercise. And I'll see you at school. Hopefully I don't have to say that again. Bye.